Alright, this is topic 5.3, electric cells of the IB Physics curriculum. So, a quick overview of 5.3, investigating practical electrical cells, both primary and secondary, describing the charge characteristics of a simple cell, identifying the direction of current flow required to recharge a cell, determining internal resistance experimentally, and solving problems involving EMF, internal resistance, and other electrical quantities. So let's start first out talking about what is an electric cell. An electric cell is a device that converts chemical energy into electrical energy, and cells are a form of EMF source. All right, what is an EMF source? Well, EMF is the energy per unit charge, which we now from topic 5.1 we call is the voltage. All right, and so it's not a force. It's weird that we call it a force, but it's not a force. It's just energy per unit charge. So it's what pushes the electron through the difference given. For example, electrons are attracted to the positive, right? So that electric field or that cell will give the energy, the potential to move from the negative to the positive. Alright, it's measured in volts because, once again, it is the work per unit charge, and therefore the work per unit charge is also the power over the current. Alright, so EMF is work per unit charge, which can also be broken down to power divided by the current. There are two types of cells that you're going to come across in topic 5.3. A primary cell, which is an electric cell that can only be used once until it runs out, and a secondary cell that can be recharged and used again often many times. Now, is it infinitely in its lifetime? No, because each time you recharge it, you get a little bit less out of it, and that goes into a topic way beyond the scope of this class. We talk about entropy, and some energy is always lost, but once again, not part of this topic, so we're going to ignore it for now. But just a little side note to think about. Alright, and so method of charging cells differs depending on the type of electrical cell. So chemical batteries is to reverse the chemical process inside the battery. So you plug in, you plug in your laptop, whatever, the energy from the outlet sends the charges back, reversing the chemical process, and this is what we use inside our phones and laptops, etc. When charging a secondary cell, the current flows in the opposite direction than when the cell is being used in its normal operating mode. So, for example, right, normally we expect the conventional current to go this way, but instead it is going to be going the opposite direction from positive to negative. Here's our recharging circuit, and here's our current when it's normally being flown. Alright, so consider a circuit that is charging a 2.0 volt battery. Find the current in the circuit, find the power dissipated in the battery, and find the power restored to the 2.4 battery. Alright, so for A, for Kirchhoff's laws, we have the current, right? Remember that V equals I times R. And because this is a series circuit, is one loop, the current is going to be the same through each element. That's Kirchhoff's laws. If you don't remember Kirchhoff's laws, go back to topic 5.2, please. Alright, and so once again, the voltage across this resistor is going to be, 2 times I, the current, because V goes I times R, and likewise for everything else. Now, normally a voltage drop across a battery is positive. However, when the secondary cell, because it's being recharged, the voltage drop is going to be similar to that to a resistor, so it's going to be negative. So you have a positive voltage drop across the 12 volt battery, and of course we know resistors have a negative voltage drop. And this battery here is going to be a negative voltage drop because it's consuming power and not providing it. And so Kirchhoff's second law says that the total voltage drop across the loop must be equal to 0. And so solving this, you get I equals 10 over 16, and so 0.625 amps is the current. And once again, that's going to be the current through every element because there's only one loop. And so to find the power dissipated in the 12 volt battery, we have P equals I times V. Well, I is 0.625. The voltage of the battery is 12, so 7.5 watts. Now, the power dissipated in the 2-volt battery, same thing, power equals I times V, so we get negative 1.25 watts. And once again, we get the current a negative side in this case for part C, because it's basically going the wrong direction as if it was providing power. So it's a negative power drop. All right, and so the internal resistance of a battery is the next main topic of topic 5.3, and it's really actually the major topic of 5.3. And so far, we talked about topic 5.1, but a lot in topic 5.2. We dealt with a lot with batteries, and we consider those ideal batteries. But however, in real life, batteries aren't 100% efficient. They have some internal resistance that loses some type of energy in the battery. And so we call what the voltage actually gets out is the terminal potential difference. And that is measured in volts, all right? So the ideal EMF would be your 9-volt battery, but when you plug in that 9-volt battery, what you're going to get is maybe 8.5 volts because you lose some of the energy to the internal resistance of the battery itself. All right, and this is a nice equation in your data booklet that says that the voltage equals epsilon minus the current times the resistance, the internal resistance of the battery. And so an ideal battery, if R equals 0, then of course then you should get the voltage out. But once again, real batteries don't have 0 internal resistance. Alright, so let's take a look here of example problem. The potential difference across the terminals of a battery is 4.8 volts. When the current is 1.2 amps and 4.4 volts is 1.4 amps. Determine the EMF of the battery and internal resistance. So we need to use our equation twice. We have two unknowns, so we need two equations. And this becomes a system of linear equations. 4.8 equals epsilon minus 1.2r. 4.4 equals epsilon minus 1.4r. Subtracting the bottom equation from the top equation, we get 0.4 equals 0.2r. R equals 2.0 ohms. And then to find the EMF of the battery, we can simply plug in r, little r, into any of our equations that we want and get a value for epsilon. And so plug into the first equation, we get 7.2. Now, if I plug it into the second equation, I would have got the exact same answer. So it doesn't matter which equation you choose, as long as you just plug in the correct value for r. Alright, the last thing they want to know is the capacity of the cell is the amount of charge it can deliver in the external circuit in its lifetime. Alright, and so first things you need to know. One, the larger the current, the faster the battery discharges. That shouldn't be like odd, right? Obviously, as you draw more current is charge per unit time. And so if you draw more current, that means you're drawing more charge in less time. So it makes sense that the battery's going to decrease, right? Faster. I mean, for example, velocity is distance per unit time. If I go a greater distance in less time, I'm going to get there faster. Same thing with current. If you draw more charge per unit time, you're going to discharge the battery faster. So that should not be a strange concept, but it's one that you do need to know for the IB exam. A second one here is that basically ideal battery would eventually like have the same output and eventually drop to 0 at the end of its life. But once again, as I mentioned before, that doesn't really happen in real life because each time you charge a cell, you get a little bit less out of it. And so you may get 12 volts for a small portion of it, and then you may get like 11 volts and 10 volts and 8 volts and then eventually 0. So an ideal one would have the internal voltage be the same, and then when it runs out, drop to 0. But we know that over time, the battery slowly loses its potential difference. That is the difference between an ideal battery and a terminal battery. Alright, and those are the main topics and concepts you need to know for topic 5.3.